All right. Thank you everyone for your patience, and thank you very much to the organizers of this event and the Geological Society of Australia, WA Division. Thanks Ryan and Sandra for inviting me today to talk about cracking the code of Earth stress. A piece of work that we've been working on with Poulet, standing over there, the star of the event. So if there's anything good that you like in these presentations, feel free to pay him a beer, because he contributed a lot. I'll happily take all the negative comments, can be responsible for that. So before I start, I'd like to acknowledge the Whadjuk people from the Noongar Nation as the traditional owners of the land that we're meeting on today, and pay my respects to their elders past and present. So this long title you've seen really can be summarized in 2 words: fault slip, right? That's the whole idea. And I doubt that I need to convince anybody about the critical importance of faults in geosciences. So whether you're coming from, perspective of natural resources exploration, engineering and infrastructure, or just any other, kind of structural geology, tectonics, every field of geology is interested in faults. There's no doubt about this. And one of the important aspects is that the faults have a wide range of behaviors. So on normal days, some of you who might know me might know that I really enjoy one end of the spectrum, which is looking at the very complex side of the multiphysics of faults. And that's going to be for another day. So today, no multiphysics, no thermohydro, mechanical, chemical shear zones with episodic stick slips and subduction zones and mega thrust and fluid pumping from depth. That's for another day. Today, we'd like to look at the other side, the other end member, to look at something that is more common, because these complex ones are very specific. What are the behaviors of faults that are the most common? And basically, what is the common denominator between all the faults? The simplest one is just geomechanics. So today, it's geomechanics only, as we define the faults, at the interface, the slip interface between 2 blocks, 2 rocks that at some point have been moving once against the other. And that means that we can boil down the whole story on the theory of friction. What is a friction coefficient? That's pretty simple. We're looking at the ratio of the shear stress over the normal stress. And based on the picture, you can already guess that this is not, very novel science. People have been doing this for a long time. Some nice pictures from Byerly, looking at various rocks. So the shear stress, how much we put on the rock on the table. The normal stress is the gravity pushing, in contact the 2 sides of it. And one obviously is facilitating the slip, the other one is preventing it. And what happens is that when you plot in experiments for rocks, you get a very linear relationship. When you plot it for a lot of rocks, you get this kind of pictures. And maybe I should put my pointer. If I find the screen. Up, no, right, no, yeah, here it is, tiny pointer there. So that's what it is. Very simple principles and very well documented. That's all kind of depth. So we know all of this. Now, the friction coefficient is defined by the maximum shear stress. We're talking about for the static, coefficient of static friction. We're talking about the time at which we pull enough that it starts moving. But for most of the faults, it doesn't have to be moving. So what's interesting is to look at what we call the slip tendency analysis, where we look at the current shear stress. And if you look at the current shear stress, it could be anywhere in the space, plotting the shear stress versus the normal stress. And the closest, the highest we go in terms of shear stress, at some point we might hit this critical line, which is defined by the friction coefficient, and the fault will slip. So that is pretty simple. That's good. And all we need to understand all of this are 2 components, the stresses, but we're talking about the full stresses to have access to the normal stress and the shear stress based on the orientation of the faults, and the friction coefficient. So let's start with the friction coefficient. Really, what values should it take? That is a good question. And like many questions in geoscience, the answer is, well, it depends. So 0.85, we just saw that was an upper limit for different kind of rocks. So that's great. We have an upper limit, but what is it really? Well, we know it's depth dependent, and we know that a lot of people have spent a lot of time doing experiments. So if you were to ask an experimentalist, they probably would tell you, well, the value is 0.65. Right, for most rocks, for most intact rocks under dry conditions. But of course, it's not all of that. There's a whole range. It can be a lot lower for different rocks. And if you look at some talc, some schists, some clays, it can be a lot lower than that. And it just happens to be the ones you actually find as fault gouges, just by coincidence. So that becomes a bit more complex of what happens. And of course, this is all for intact rocks, which is not usually what you find in fault environments. And then, of course, then you start piling up. There's the anisotropy effects, and then the pore pressure event was that we don't talk about multi-physics. I needed to mention this one at least, because that plays such a critical role. And then your faults can be creeping, so it can be static or dynamic. Long story short, we can't really generalize. So because we can't generalize, there's a whole area of science that's cryptology for you, people spending their lives looking at just that, so I'll leave them do that. But not everything is lost, because we can basically decorrelate the problem of understanding the stresses and then putting a friction coefficient as the limit at which the fault is going to slip. So that means that we can look at the stresses and say, okay, the closer we get to our limit, the closer it's going to slip. If we don't know what that limit is, as first approximation doesn't really matter because we can go as high. The important part is that the higher we go, the worse it gets in terms of slip. And we can defer the choice of picking an exact friction coefficient to people who are looking at specific faults. So for today, we are looking only at the stresses and looking at this slip tendency index. And the higher it gets, the worse it is in terms of potential to slip. So let's look at the stresses now. The stresses, we're talking about the full stresses. So in 3D, we've got the three principal values, and then you've got all possible rotations of it. That's 6 degrees of freedom. So do we know all the full stresses on the ground everywhere? Short answer, no. That is quite complex. So how far can we go towards understanding all of this? Well, it's often assumed that one of the directions is the vertical directions, because gravity can play a major role, like in sedimentary basins. So people look at having a principal, maximum horizontal stress, minimum horizontal stress, and one of them is vertical. So now you only have one possible rotations, 3 stresses, that's 4 degrees of freedom. So we lost 2, that's great. Then next, we can actually somehow easily estimate the stress directions. And I'll talk more about this in a minute. So that gives us one more constraint, so that's we basically boiling down to 3 in a way. And then what about the rest? And that's where it gets hard. So there's some amazingly good work that can be done, but only for very specific cases. So in case you haven't seen that one, I highly encourage you to have a look at it from Choi et al. The Korean team looking at some nice post-mortem analysis, forensic investigation of faults that has slipped, looking at all kind of experiments, lots of information, lots of data, lots of really, really good work. And they can basically put all of this in one graph and constrain for one friction coefficient, exactly a very tiny area for the horizontal stresses in there. Excellent work, fantastic. That is for one fault that has slipped, for which you've got all the experiments available and a lot of time to proceed. So the next question is, well, what happens if we want a slip analysis on a wider area, right, for larger areas? So if you want to do that, the real way to get there is to use geomechanical simulations. That is the current way to do that. So for that, you pick up rheology, and usually people look at commonly at linear elasticity, because you can homogenize all the properties of the parameters, making effective properties. And we know the equations. That's pretty easy to solve. So you just have to build a full 3D model with every single rock units and find all the material properties for every single rock units. What more? That's pretty easy, or not. But that's doable, right? So a lot of people do that, and you need to define them the boundary conditions. And this is one of the aspects that is often neglected, because when people see some numerical simulations, it's usually mentioned saying, oh, this is what we impose, but very rarely do people ask, why exactly do you pick those boundary conditions? And there's very poor constraints on that. And obviously the results highly depend on those choices. So this is one of the examples coming from Germany, where this is the whole country, the whole of Germany, and they're looking at different ways of defining the slip tendency. That's not what is important in there. But what I wanted to show you is that this is a real 3D analysis. So they build a whole 3D model of Germany as precise as they can. So this is building on decades of work with all the material properties, literature review and everything else. Apply, simulate, get the stresses. And from that, you can input your network of faults and get some slip tendency, which is a 3D problem. And you can see if you pick one particular fault, you can really see that it has a depth evolution into it. Okay, so the third dimension is important. However, hopefully you can see that looking at this as first glance, you can see that the 2D approximation is good enough to get a good understanding of which faults compared to others are more likely to be slipping under the assumption of a friction coefficient. So this is an example done in Germany by Mojtaba Rajabi at UQ to show you that it can be very expensive. This model has several million degrees of freedom. dozens and dozens of different rock units, each of them, with an extensive literature review to calibrate against a lot of data. Fantastic work again, but still very expensive and highly uncertain. So the question is, can we generalize? Can we speed up the process? We all know it's always a trade-off between accuracy and speed. So I've shown you that we can get some relatively accurate models, but they're very, very specific, takes a lot of time, a lot of work. So the question is, can we go on the other side? Can we get something that is more generic, faster, cheaper? Because obviously I'm one of those people, rather in a hurry. So what do we know about the stresses? We are lucky because of some nice initiatives also coming from Germany, which is the World Stress Map project. You might all be aware of this. People have been assembling, a whole team of people, this really fantastic data sets of a lot of stress orientation information all around the world. That's coming from borehole breakouts mainly, but also, drilling-induced tensile fractures, overcurrent tests when they can afford the experiments, some earthquake focal mechanisms, hydraulic fractures, whatever geology they have available. This is really, really great. Lots of data, dense data sets, fantastic. Let's have a quick look at the quality of it. The quality is great for a stress direction analysis, meaning that, we can download this database, plot it in GIS, with or without help of friends. Thank you, Vince. And, look at color coding them by quality. The best quality they've got is plus or minus 15 degrees. That's pretty good. That's pretty accurate, but it still makes a 30-degree, cone out of 360. That's about 8% uncertainty. It's all right, but it's not machine precision, put it this way. On top of this, we just talked about the fact there is a depth dependency to it. So we cannot neglect the fact that stresses vary a lot with depth. And when you plot this into a 2D map, you have to account for this. And finally, even if you knew very well with perfect accuracy your measurements, there is definitely a very large variation of stress locally, okay? You just have to think of a couple of rocks of different competencies. One of them is indenting onto the other. The stress patterns you're gonna get are gonna be very local and varying a lot in directions. So that means that any observation you see cannot be generalized everywhere. So we need to look at averages, and for that we need to look at a scale that is large enough that we have averages to work with. In our case, that means we're going to work at the continental scale. So luckily, we've got dense enough data sets that we can actually do that. Now, just to mention, you can also look individually, but then you have to go back to what I was talking about, picking a 3D model with full definition of every single thing you have, which you can do only for specific analysis. This large scale means you're working with geostatistics, and the current state of the art is coming from Rajavi and his group, looking at the World Stress Map in Australia, where there's plenty of data, enough to look at it and say that things are very localized. They're localized by some provinces. So what you can do is pick the whatever it is, about 30 of them. In each of these provinces, you just average all the stresses, gives you one of those red markers on the map on the right-hand side. And then we used a bit of kriging, Poya, press the button, and here it is. You get some map of the best estimates of the stress orientations, the maximum compression direction in Australia. Very useful, for sure. But that doesn't answer our question. So today, what we really want to talk about is, can we get to the next step? Can we get the full stress from this stress orientation, other than the manual calibration we just talked about? So that's the challenge for today. Spoiler alert, the answer is yes. We do this using physics-based machine learning. So everybody knows about machine learning. Not everybody might know about the physics-informed machine learning. So what do we mean by that? If you pick a problem that's, is something that can be described with some physical equations, like a mass at the end of a spring that's oscillating, and you're plotting its behavior in time, there's different ways of training a machine learning model, a neural network, to actually match this. So the orange dots represents your observations. You've got at the beginning, at a few intervals, the exact position of the mass, and then you wonder what happens next. If you train your basic machine learning, a neural network model that you use to figure out if this picture is your neighbor's cat, it's fantastic. It matches very well your data, but it does not have any extrapolation power. So you cannot go very far. So instead, what you can do is that you can add some points, some collocation points, as the green points, where instead of imposing the constraints on what you observe, we're going to impose the constraints on the equation that we think, drives the underlying system. And if you do this, then with the constraints and the equation everywhere else, you can get a very, very good analysis and prediction of the whole answer of the system. So in other words, you can use machine learning pretty much like a forward simulator. So let's look at this and let's compare the two. They both work with the same system of equations. And as I said today, that's the very little math there would be. So forget about all of this. That's, for those who want, it's just linear elasticity. Pretty simple. Okay, something that we can solve. We've been solving for a long time. Put your momentum balance, some constitutive law, small deformation. So we can solve it with a traditional forward simulator or with the physics-informed machine learning approach, those pins. So what does that involve? The forward simulator basically starts with setting up a mesh, usually, depending on which numerical scheme you're going to pick. But let's say we're working with something like the finite element methods. You build up your mesh, you set up your numerics, you solve it in a deterministic way. The system is very well known, very well behaved, so we can fully control the accuracy and get very close to machine precision. Fantastic. Now, on the other side, with the machine learning approach, which is more, newer, you set up your collocation points nearly everywhere as well, but you don't need to build a mesh. Now, the dark art resides somewhere. In this case, it's about setting your network architecture, and you set up your loss function. So you're going to minimize something. So you want to minimize your constraints, your constraints on displacement, constraints on stress, and constraints that you want your equations to hold in the whole domain. And you put all of this as a loss function. You want to minimize it, use some optimization. It kind of works. If it converges, playing with the dark art of making it work, but you can make it work, just not exactly with the same accuracy. Very good accuracy, but not machine precision. So if I leave the story there, obviously you're going to tell me, well, what's the point? Because the forward simulator wins hands down, which is true, but that's not the whole story. The whole story is that after you can solve something, you then need to look at your parameters, which in this case, we've got a couple of elastic constants for the linear elasticity problem, and you need to calibrate them to work towards matching your real data. And this is where it starts getting really hard. For one domain, 2 parameters, easy. For the dozens of domains I was talking about, you've got, that times 2, that's a lot harder, which is why I tip my hat to people who've done those big 3D models of, in Australia, because it's a lot of work of calibration to make things work. As opposed to if you go on the other side, what's really neat about the machine learning approach is that it integrates the parameter optimization for you. For barely any extra cost, you can throw in there the fact that those parameters are unknowns as a distribution in space and let the whole system solve it. So you have a bit less accuracy, but it solves the whole problem by identifying the spatial distribution of your material parameters to actually fit your constraints. And that is a game changer. And this is why it's very, very interesting to take some approaches like this. And of course, hoping that, the accuracy will improve in time. And there's lots of other work that at some point, maybe Poulet can give a talk on the technical bits on how to make this better. So if you want to know more about those two, I recommend a nice Nature paper by Shen and others that came out last year, looking basically at how, from a more philosophical perspective, if you wish, we can marry this forward simulator approach, what they call the process-based modeling approach, with the machine learning, which they call the differentiable programming approach. And they mix the two to make it a differentiable modeling approach. And you can read faster than I can talk, so I'll let you read some of this if you want. Have a look at the paper. But basically, you can see in green that the forward simulator is very good for interpretation. We use those simulators because we want to understand, okay? We want to interpret, and we can do this on conceptual models, even without data, to understand the concepts, right? On the other side, machine learning is very good to match, to calibrate, and therefore to predict. So the nice bit, though, is that there is, some nice combinations of some synergies between the two that are in orange. And what that means is that you can basically bring some interpretability to your machine learning approach. And that's the really interesting part of it, because identifying pictures of cats is fantastic when it works. But if it works or not, you have no idea why it does or why it doesn't. So, apart from having a good accuracy in general, it's not very satisfying from a scientific perspective. And what the authors are talking about is that you can look at your problem from 2 different perspectives. So the graph on the left, the diagram, shows you this kind of topography, which is your searchable function space. We are looking for the minimum, which is the optimal function located here. And the process-based usually does not allow us to get there because we don't have enough parameters. We play with conceptual and simple definitions. We cannot get to the exact match. On the other side, the domain for the machine learning in blue is very big because we can capture pretty much everything. But it's a bigger space and we're not going to get there as fast and we're going to get there with the same accuracy. But by marrying the two, you can either see this as a machine learning model okay, that has been guided into a smaller searchable space, or you can look at this as your process models that has been expanded search space to match this, which is a very nice way conceptually to marry the two. And in other words, the conclusion is we can hopefully get the best of both worlds. And that's what we're about today. So in practice, what are we talking about? Here's one of the benchmarks. And that just shows you what we're talking. You can ignore all of this if you want. That's probably one slide you might want to ignore. But just to show you that you design your neural network, that from location of X and Y in these 2D problems, you're gonna predict the displacement in X and Y and the stresses, the 3 stresses you need for your 2D configuration. That's what the loss function looks like for those who want to look at it. The first line is defining the constraints on your displacements, X and Y. The next 2 lines are defining your stresses, whether you have stress constraints, and then you just define the equations you want to hold, your momentum balance, your constitutive equations, just as terms, and you want to minimize all of this, let your neural network do the work, and hopefully it works. So these authors have shown, Hagigat and al, that you can pick one of those benchmarks for which we have an analytical solution, and it does work, which is great. Not machine precision, but very good and definitely very interesting. So we've reproduced this, playing with it, but this time we've added a term to the loss function. This time we are looking at constraining the stress orientations because this is the data that we have available. So picking a few scenarios, 7 of them. First case is being mangled. That's Windows reading my Mac PowerPoint, but that's all right. You can guess what it is. These are the boundary conditions you were just looking at. Were the previous one? No, that was because of the picture. That's those boundary conditions, right? So you've got some displacements, you've got some stresses on the sides, on the top, and displacements at the bottom. So if we pick all of this, this is what the displacement in X and the displacement in Y look like, just to see by comparison. And this is pretty much the analytical solution. Fantastic, tick. Now, second scenario, let's add the stress orientation. Analytical solution, we know exactly what the stress is supposed to look like analytically. So we can put this in there, and at every point collocation in the domain, we can do this. Same results, fantastic, that's a tick. Of course, we added information, so it cannot hopefully get too much worse. But because we added information, now we can start removing some of the constraints. These are the boundary conditions. So case 3, we are removing the stress boundary conditions, still works. So let's continue removing things, removing the displacement everywhere but at the bottom, it still works. And removing it, keeping only the displacements in 2 points at the bottom, still works. 2 other points, still works. So in other words, it really works, pretty much everywhere. And just to confirm, we're not mocking up with something that always works. If we remove the stress orientation, we are defining a different problem because with the same equation but different boundary conditions, it's a different problem. So we have a different solution, which is what we retrieve. So this was a really big step forward for us because we understood that we could actually replace the boundary conditions by the constraints on the collocation points of your stress orientation. And that is fantastic because we have no idea about the boundary conditions in real life in Australia, what's the real stresses applied to the continent and the real velocities, but we can have a good understanding of those stresses. So equipped with this, move next, but that does require a minimum of displacement constraints. So that raises the question, what displacement constraints do we know in Australia? Luckily, the answer is quite a lot as well, because we have all this GNSS network that's deployed, this global navigation satellite system that you're using to Google your way to this meeting today. Constellation of satellites, plenty of GNSS stations all over the world, which is fantastic. That means a lot of data available. Some places like San Andreas Fault, obviously it's peppered with them, so you have a lot, very dense data sets. But even in Australia, we still have a few, which is nice. And that allows you to basically sit on your couch, have some popcorn, and watch in real time plate tectonics. Can you see Australia rushing to Papua New Guinea? I see Vince super excited. That's what he does every Sunday. So we don't have that much data in Australia, but what we do have is very good data because of the seismic stability of the continent. If you look at whatever in Perth, for example, the last 30 years, it's as steady as it can get, which is fantastic because that means that I'm just putting this number bigger in here. We can get a precision of usually less than 0.1% in most of the stations in Australia. And the worst, I think, in Australia is still better than 1%. So that's 2 orders of magnitude better than the quality we're getting on the stress orientation, which for numerical purposes is very interesting. And then if you remove the general trend of us getting towards Papua New Guinea and we pin on the board Alice, as a displacement, you can really see very nicely the compression east-west from the whole continent from the other station, right? So this is quite interesting and very useful. So that brings the question, which constraints should we use then? Should we use the stress orientation? There are lots of them, but they're not necessarily so accurate. Or should we use the displacement? Very accurate, but very sparse, only, a dozen or so plus data sets. And the trick is that they are linked because stress and displacement are fully linked by the geomechanical model. So we don't really have the flexibility to pick one or the other. We should pick both, but do they have to match? Are they consistent? That's the question. So to answer this, we're going to get one at a time, take the end members first. So starting from the stress orientation, let me try to explain what you are looking at. You're looking at roughly Australia. Hopefully you will have all recognized this bit. And the black markers are showing you the stress orientations that we retrieve from the model. So the dark black markers are showing you that we retrieve, this is what we impose in this case, all the constraints. So pretty good that we do retrieve what we put in, right? So that's not a surprise. But we also retrieve the arrows, and these are all the velocities, the displacements that we retrieve from the deformation of Australia. And the red arrows are the 16 or so constraints that we took from the NASA observations. And what you can see is that we still had to remember to put a couple, at least for the boundary, to constrain somewhere. So I think I picked Perth and Sydney, right? So around Perth and Sydney, the arrows match really nicely. The gray arrows match the red ones. That's because that's what we imposed. Everywhere else, it's a very poor match. Okay, so just taking the stresses orientation is not going to be enough. So let's look at the other side for the other end member. This time we ignore completely the stresses and we impose the constraints just on the displacements. So we pick no stresses whatsoever, but we impose our 16 velocities. And what we do retrieve this time that is physically consistent is a velocity field that matches nicely what you would expect to kind of interpolate what you have. And however, it will pick the easiest, the smoothest stress field that will allow us to match this. And what we do retrieve is pretty much this east-west compression of the continent. So we could match all the velocities nicely just with a simple compression of Australia. So these are two end members. The truth is somewhere in between. So for our best guess, what we did is to actually mix the constraints. And we took all the displacements, the 16 displacements in red, and we took the whatever 30 or so provinces that we had for the stress orientations as constrained as well. And then we're actually letting the system determine for us how well it can converge, playing a bit with the dark magic to get results as good as we can. But we know that the problem is ill-posed because there is no reason why our data, which is imperfect, will absolutely match the perfect solution that is physically consistent that we're looking for. And what is nice about this approach is that we can see that we retrieve the very good velocity distribution that matches all of our orientations. But for the stresses, it is no longer a simple compression east-west. It is much closer to what you would expect based on the constraints we pushed, but it is not a perfect match with, in this case, the red ones, which are my 30 average stress orientations. But those stress orientations were geostatistics. We don't know if they're really representative. We don't know what accuracy they've got. There's a lot of question marks. So what is very interesting to see is that we get something that is on the plus side, has this physical consistency to it. So we can actually derive some real conclusions about what happens. We can see areas that match reasonably well, areas that don't match so well. So for example, the Northern Territory, with the data set that we have at that resolution, we know that this is not something that we should take for granted as, very likely to be like this. It's very unlikely that we have the correct, stress orientations at that scale for the whole Northern Territory. And we can identify the zones of discrepancy. And I didn't mention it, but I should. We also retrieve the maps of the couple of elastic constants that we wanted for the system in order to produce those results. And what is particularly interesting is to look at the Young's modulus, because it basically shows that we have this rock strength increase from the east coast to the west coast, and that these in agreement with the variation of the lithosphere thickness variation with age in Australia that's been published before. So you got the Phanerozoic on the east, and Proterozoic in the center, and all the Archean on the west, and the thickness increases with age, and we do retrieve this behavior, which is very interesting. So we have some match, we have some explainability, which is interesting. But the result is not perfect, but it tells us where it is not. So we can already derive some of the conclusions from geodynamics modeling, at least in Australia. You all know this quote probably really well. Hear it all the time from Samuel Carlin. And that was written way before we had machine learning. So I would be tempted to modify it to say that the purpose of model is not just to fit the data, because today we can fit the data really well with machine learning, but it's to sharpen the questions. And that's your interpretability, your explainability that we want to bring with the physical process that we include in the machine learning. So we showed you that we've brought in a brand new approach that allows us to infer the geodynamic stresses from observations. We can get the full stresses pretty much at the press of a button. A bit of dark art, of course, of numerics behind the scene, but it's pretty much as automatic as it gets based on the GNS data, as well as the stress orientation, and we have quite a bit of it. We can identify the discrepancies in the areas that need more analysis, which is interesting. Some people might say, look, the answer is always the same, just get more data. And yes, by all means, get more data. So those of you who have access, please get us more data, but there's more that we can do than that. And we should look at to getting more reliable averages. And based on these kind of approaches, we can push the investigations a lot further. We can start looking at the local variations, improving the resolution, and start matching, you know, as a scale from top down, getting some much better understanding. Also, more GNSS stations will help, that's for sure. And but we nonetheless were able to retrieve the displacements that are, you know, physically consistent with the best of our knowledge with the data we have available all around Australia. That means that these conditions can then be imposed for people who do want to run some numerical models in terms of stresses or displacements. As we talked about, we can actually provide some proper boundary conditions, and that's a big step forward as well. So we were able to identify where the model was not fitting. That's the discrepancies. That also means that we obviously identify the models where it does fit. Where it does fit, then we can do this top-down approach and look at the next scale down to go towards our slip tendency analysis, which is what we started from. To pick as an example, the Eyre Peninsula, so focusing in South Australia. If you ask me why, the answer is probably why not. There's a lot of data, which is great. And there's also other reasons I'll show you in a second. So we can go to CSIRO, the South Australian Resources Information Gateway, pull a lot of data from there, get all the network of faults they've got available. I don't discriminate, so it's just a network of faults, not talking at all about which faults for today. And the question is, can we get a slip tendency analysis from that without doing any of the 3D expensive modeling we've been talking about? So we're going to pick this into a bigger zone. And in that bigger zone, we want to run the analysis we talked about previously to understand what are the full stresses in that zone, just taking something bigger to avoid having some boundary effects, you know, affecting the small zone that we are really interested in. And what kind of displacement and stress information do we have available? Well, that's the same I showed you before. We just zoom in and we can see that we have 3 stations. This is also why we picked that size. So we have those 3 data sets, which are so important to have this, you know, constraints in terms of displacement. These are 3 NASA velocity stations, which is great. And we have also all of these world stress data measurements available, color-coded by quality. So we take for the displacement constraints the 3 data sets, the 3 data points that we have. And for the stresses, basically pick all the quality A's and B's available in that graph. And these are shown by these little white markers. That's all the A's and B's. When there's a lot of them, just, you know, pick one of them as an average. And then there's a big question, which is what is on Earth happening here? Okay, and you look at this and you go, all right, it's pretty much 360 degrees. So averaging is useful, but only so much. So we do need, you know, it's not fully automatic because we do need some interpretation. The real answer is obviously, well, somebody needs to zoom in because there's a lot of complexity happening there. But then who says zooming in says, you know, a lot more complexity, you need to introduce a lot more variables. What if we want the average at that scale? So for that, what we did is we introduce a new data set. This is made up, completely made up, the white marker here. And it's made up because of some other information available I didn't mention yet, and that's the earthquakes. So we can see in the zone all the earthquakes from, I remember, 1840 to 2017 or something like that. And what you can see is that basically defines some kind of a, you know, vertical trend on this map. So it's like, you know, south-southwest, north-northeast kind of a trend. So because of the link between, you know, the shear and the earthquakes and the stresses, it would be nice to interpret these readings of the stresses on the left as saying that there is a zone where you can see the stresses are pretty horizontal, and then there's the bottom part of the picture where it's pretty oblique. And the interface, you know, could be along an interface, like this. But with the earthquakes being 90 degrees from that, it would be nice to have something. So this is why we introduced this point in here, but just to show you how we can play the game and push the investigation the next step. And what you get from that is what you expect, which is a model that very nicely matches the velocity fields of the 3 points that we have, and also very nicely matches all the stress orientation. So those ellipses shows you basically all the stress values, the full stress tensors in 2D at every point. And then we can look for every stress ellipse, we can look at the orientation, the azimuth of the maximum compression direction. We can paint this by colors. And if we choose a nice color scheme, you can see basically the ISO values, and you can see that in this area, the gradient is following, the direction that we wanted, which is why we picked that point. I'm not saying this is exactly what happens. It's showing you the methodology and how we can use it. And a lot more should be done at a much finer scale to, refine. But at that scale, we get some really nice approximation. The nice bit is that having then the full stresses, you just press the button and you get some slip tendency analysis. So with all the caveats mentioned before, I wouldn't put my head, relying on the validity of this data, but certainly qualitatively, as an interpretation of comparison between different faults and which one is more likely, is under more stress than which other one, this is a very nice, reliable method that works pretty much automatically from the data. And you can play on the constraints at the geological levels to understand the game and obtain something without having to worry about all the numerics behind it. And that's not the end, because in this case, we picked that big box because we had those 3, velocity NASA stations. But in most of Australia, we don't. So how do we do if we don't? Well, we can play the game to investigate that, pretend we don't have those 3, ignore them, pretend we don't know them. And then we use the model that we run at the large scale, the continental scale, which is symbolized in here by, having this coarse grid all over Australia, that gave us some velocities or displacements that we're going to impose at the 4 corners of our new smaller box, in which we run, a smaller machine learning model in there. And what you get by doing this is something that's qualitatively gives a pretty decent picture looking quite similar to the previous one. And if we then run the slip latency for that, this is what we get. If we compare to the previous one, it's not at all the same quantitatively, but qualitatively in terms of comparison of which faults, are more likely, redder. There's a lot of similarities, which is very encouraging because we can get an answer even without the so critical importance GNSS information by playing this multi-scale game of the large scale to the smaller scale, which is very encouraging because that opens the door to running this pretty much everywhere in Australia, and the caveats of the large model itself matching, in the areas where it does. Now, why with stresses that look so similar are the results so different? This is the important to show you that the results are very sensitive to the stress. No surprise there for those who understand, the math behind. But in here, what we do is that we take 10 scenarios where we change the ratio of the principal stresses. So we take this ellipse and we just change this different, the ratios from 0.1 to 1. And we look for each of those scenarios in colors, the evolution of the slip tendency in the vertical axis as a function of the angle between the maximum stress direction and the fault. Take a fault in all possible angles. This is what you get. And what you see is that if you pick, let's say, 0.3 and 0.4, the colors are pretty much the same. Those pictures might look visually quite similar to you. And yet 0.3 and 0.4, the values go from 0.45 to 0.65, which is a big numerical jump. So it is very sensitive. That is the nature of the game, which is why the results need to be interpreted. But this is really good for what we can do. So the next one and the last results I want to talk to you about today is the fact that we can control the resolution. I've talked a lot about this multi-scale. I wanted to show you that we can change the density of the grid of collocation points. So this is whatever it is, 16 by 16, I think, 24 by 24, 32 by 32, and we are retrieving the same picture every time, and therefore very similar slip tendency analysis. And what's nice, if you get a grid that is dense enough, then your results actually converge, which is what you numerically want to achieve, so that you've got some satisfaction that you understand what you're doing is correct. So that is it for today. The conclusions are that we did manage to bring a pretty much automatic fault slip analysis that can be done at a large scale. It certainly still carries some uncertainty, and I talked to you a lot about the stresses and the friction, but I'm sure that most of you could take my spot and spend a whole hour talking about the certainty about the fault locations or, the unknown geometries in terms of depth, what's happening in 3D. That adds to the problem, obviously. But, it's very positive because we can obtain some meaningful results and we can get this very fast in 2D using the physics-based machine learning, and that's a big step forward, we think. So we can, among others, alleviate the problem of the boundary conditions. That is, so important for running the forward simulations that are still very relevant, especially if we want to go to 3D and accurate, local areas. There is no way around that. And I lost the mouse instead. Click somewhere. We can identify where the stress orientation models should be reassessed, like the Northern Territory. This is also another important aspect of it, because everybody knows that it's imperfect. The real question is, where should we look? And that we can answer with this kind of approach. And even if it's still uncertain, it's a lot better controlled than deterministic approaches than any other available method. And also for those who want to play the probabilistic game, okay, we can start playing the probabilistic game by looking at constraining the observations and getting the results through this approach rather than using purely geostatistical distributions as it is currently done. And I'll finish by saying that, the velocities are really, really important. So it'd be fantastic to get more GNSS data, even though Australia is very seismically stable. But even if we don't, we can play this multi-scale game and still get some nice results. So all of this, the first part of the stresses just came out in December. We published this with Poulet in Scientific Reports, and the sleep tendency analysis for those who are interested, hopefully will come out at some point. It's currently under review. On that note, I thank you very much for your attention.
Thanks. Thank you, Thomas. Any questions?
No, beer time. So
how do you choose the location points for sampling loss function?
The short answer is you want to put as many as you can. So the ones we have constrained, whether it's velocity or stresses, they're determined by where you have your constraints. And for everything else, you want to put it, as many as you can. But if you put too many, you are over constraining the system, allowing it to make some, very sharp variations to fit your data. And therefore you might artificially introduce all these, negative effects. So ideally you want to put as much as necessary without putting too many that over constrain your system. So there's still some dark arts, there's a bit of playing with this. But, sorry.
So my question was, how easily do you think this could be exported to study areas which are extremely densely populated and exposed to high potential for seismic activity?
That's a good question. There's no short answer, right? So the densely populated first has nothing to do, obviously, with any of this. The seismically active part, though, means that the stresses are much more likely to vary a lot more. And that means that you would have, if you want something as reliable as you would like it, you would need a lot more data. But there is quite a bit of data, right? Because if it is densely populated, chances are that you got a lot of engineering going on, and therefore you might have a lot of stress orientations, and therefore you might be able to actually see just at the naked eye some of those variations that actually have some real patterns rather than what we look at, which was this big cloud in all 360 degrees, and you go, is this because it's all garbage? My answer is most definitely not. But what's happening is that it's a zoom in. It's something that varies locally so much that's, when you zoom out, it becomes meaningless. So it has pros and cons, right? I'm quite confident that we definitely could do something because it has more data. And we were very keen with Poulet to find, we nearly embarked with a PhD student who wanted to look at something like that at an area which is denser in 3D to look at the variation. But we need somebody who would, put up the sleeves and spend dedicated amount of time to do this, because that would require quite a bit of work. But it opens that door. Sorry, Bruce, just was a question there.
How much of the variation do you say versus larger fall to the 1 million predictions statistically?
We did not process statistically any of the falls. So I would say, as Guillaume would say, ooh, there's a lot of geostatistics doors being open, with such methods. There's a lot that can be done. And this is what I wrote as one of the dot points for the conclusion, right? Which is that you could look at the whole probabilistic approach in a very different eye. So instead of putting your bell curves everywhere for the parameters, which does not necessarily really match, you can work on the physical parameters, have these produce the results and generate some probability distributions that are actually physically consistent, from which you can derive all sorts of geostatistics. So I'm really hoping that this really has a lot of avenues in front of it. Good point. Bruce.
I have several questions.
Bruce one.
One of the things that people in the mining industry really want to know is what is the magnitude of horizontal stress or Paul signal. But they also want to know what the stress is that writing us to that. And they also want to know how the stress varies in depth. And you implied that your method was capable of establishing that. So, I mean, let me be more specific. The poor old metamorphic geologists, bless their souls, believe that the stress is hydrostatic at depth, whereas if you're a real person, it's not. It's a function of the plus-on ratio. So is there a way of getting at that problem?
There is, and this is why I was saying that with Poya, we were really keen to work with that PhD student who had told us that, she was very interested into doing this. The methods inherently has no restrictions about being 2D. We are applying in 2D because our data sets are in 2D. But if you were to have a lot of dense data sets with the third dimension, the equations are just the same. Yes, computationally more expensive, but let's leave this aside for the computers. If you have enough data.
Well,
correct, but you need somebody who's going to spend the time fiddling with all of this, which is why we wanted somebody to do this. But the answer is yes, the method is amenable to that.
To get depth, stress.
Yeah.
That would be.
Yeah. So, but obviously, how much data do you need to get accurate value? And to come back to your first comments, yes, people want sigma 1 and sigma 2, but if you go back to the Korean study I was showing, which is, very nice forensic analysis, they only get, sigma 1 over sigma v and sigma 2 over sigma v. So it's always going to be about ratios mainly to get the absolute value of something that's yet a different problem. But for this analysis, the ratio is the critical part, the first order that you really want to nail. And the third dimension is very, very important, but I didn't talk all about pore pressures, which is a big component for the third dimension, which you can put in there. But again, somebody needs to do the work, and I don't want to talk about something that we haven't done yet, but it's something that we'll be very happy to do.
Another question, which is somewhat technical, is the Biley distribution of stress in the crust is not it's not a yield surface. And in fact, below that, it goes berserk because it's not concave and it doesn't obey the second law of thermodynamics and that stuff. So that you're using essentially Biley.
No.
Aren't you?
No. See why I said the Biley was mentioned to say, look, friction, because he's got this 1978. You're misinterpreting, you're looking at me and thinking of the thing I'm usually talking about, but I actually did not talk about this today. The Biley I mentioned is the 1978. Yeah.
Is that some people would say, like Sam and many others, would say it's actively going under plastic deformation.
Correct.
So how does that influence?
Let me finish first with the Biley. The mention of Biley is just 1978. The paper is called Friction of Rocks. That's the reason it's there, to show experiments. It's not got nothing to do with, all the things you just talked about, which I fully agree with you. No, nothing to do with your surface. And which is why I just said, even for the friction, it's kind of a limit, which kind of alludes to some kind of yield surface, and said, look, just ignore all of this. I'm just infinitely going up. The more shear, the more slip tendency there is, and leave the whole discussion about any kind of a yield to some other discussions that build on top of this. Very important discussions, but they build on top of this. So we need a first step before we even go there. So none of this is kind of relevant for Biley. And your question, then I forgot, the real question was?
Was about the fact is it's not only elastic.
Yes, it is absolutely plastic. And this is why I said, when we pick the elastic properties, I made sure I said it's the homogenized, the effective values. I didn't pick this up. People who are doing this analysis, the pictures you saw from Rajabi and Rokel in Germany, they are using elastic models for practical reasons because plasticity opens a whole new door. But in practice, some of them have used plasticity and get very similar values, and therefore they thought, okay, well, why can make it complex when a simple way, changing the numbers, obviously you need to change all the data that you put in your elastic model to have effective values that reflect the fact that you're homogenizing a very plastic problem with an elastic model, which by definition is fitting a square peg in a round hole. But there's ways to approximate this. It's a model.
Plastic displacement vector function of the yield of the loading. But if it's on the yield, it's a function of the yield.
Correct.
So
but
that's quite different.
It is very different, but again, we're looking at one point in time, thinking, in Australia, we don't need to look at the whole past. We don't need to look at plasticity. The short answer basically is yes, the model can account for plasticity. There are models that use the same machine learning approach with plasticity, but you are introducing a hell of a lot more information. You need your yield surface, you need your loading path, you need your history, you need all your parameters. But
they're important.
There are. The model can accommodate. The model can accommodate, which is why I'm saying I'm not putting my name saying the maps you've seen is me promising you that this is the truth. Absolutely not. We know for sure we know any of that. We're showing you that there is a method that opened the door to getting there. And now how far we need to go to get accuracy is what you're asking. Sorry? I missed that bit.
Encourages you to follow.
That's it. That's the whole idea. That's the whole idea. That's our message in the bottle. Who wants to play with this? Come and work with us. Any more questions, Vince?
I like the idea of getting sleep potential flows per day. I like the idea even more of getting sleep potential flows a billion years ago.
A bit what?
A billion years ago, like trying to understand what flow could be in the Mesoproterozoic where you might have mineralization elements. So could you use, I don't know, results from people that are doing plate tectonic modeling in terms of velocity and integrate that into the model, and based on flows that are existing today and we know were existing 1.5 billion years ago, could you
the honest answer is that this is very targeted at using current data because we have reliable stress measurements today, and we've got fantastic velocity displacement measurements today. If you want to go in the past, yes, you can build on what some others have done, but then you build on top of all of their assumptions because whatever they've done is based on assumptions. So then you kind of eating your own tail, taking their results to redo something. So to be honest, this is not the first problem I would follow up on. There's so many interesting problems we can do that we know are, of high impact and more, easier to tackle than that.
Any more questions? A lively discussion tonight. It's nice to see. All right, everyone. Thanks for that. Thanks, Thomas.
Yeah.
All right. Yep. That's all right. Thank you for coming, everyone. So our next talk will be the first Wednesday of May. Hugo Aldrich from Curtin University will be presenting Pink Diamonds, the Science Behind the Craze. Same location, same time. Thank you.
Thanks, Ryan.